So I kind of broadcast it. It is resumed. So, all right. So start from here. I mean, the user can choose different kind of fuzzy inference system model. As you can see, Mandani, Scano, Tsukamoto. If the user selects Scano, you can see a little bit difference shown up in the user interface. Because Scano and Tsukamoto, they try to let the user avoid the so-called differentiation computation because it's really costly. So for the Scano and Tsukamoto, the output definitely should be a crisp value, not fuzzy set. That is the main difference between the differences from the Mandani inference system. So if the user selects Scano, as you can see, output is an equation selection. But right now, because I did not teach you how to provide user interface to let the user code, direct code in C# programming language to specify this equation. So the alternative way is that we kind of list up all the equation we have been using in our example. So right now, if a user want to set up a Scano fuzzy inference system, not much the freedom they can do in the output equation specification. What the user can do is that simply select one equation, one output equation from the list. So that is the way we do it. But if you are familiar with the C# programming language, definitely you can provide a user interface to let the user type C# programming code to describe the formulation of that equation. But I'm not going to show you how to do that because probably you can Google that by yourself. So later on, user can freely specify their own equation somehow. But right now, it's involved too much classes in Dynamic framework, so I'm not going to show you how to do that. Instead, we just look into our example, I mean, in the textbook. So at least this equation will support the example shown up in our textbook. We can verify our inference result, I mean, in that example. So output is not fuzzy set, right? Output is an equation. So we kind of list up all the variable equation right here. So it's a little bit different, means from the Mandani system. So which means that if then rule, the conclusion part will not be the fuzzy set, should be equation specify. Let the user choose the equation here. So Scano model is a little bit different. For Tsukamoto, you need to do full proof. Because Tsukamoto model, the user must specify a conclusion fuzzy set, which is monotonic, either increasing or decreasing. The membership function that fuzzy set should be monotonic, right? So that is the only restriction for building up a Tsukamoto model, right? And as you can see, right here is in the user interface, they kind of provide another public reader here. If you use a special Mandani, right? So Mandani, the final goal is that we try to find the input-output response surface. So that means fuzzy in, fuzzy out. We like to know the output, crisp output for a fuzzy inference system. So in that case, we need to specify the type of differentiation. So differentiation type is COA, or BOA, MOM, SOM, NOM. These are the differentiation models defined in our textbooks. So we like to implement all of them to let the user select it. And how about the resulting fuzzy set? User can select cut, right? Cut inferences or scale inferences, right? So I kind of provide this kind of flag here. You can specify your own. You don't need to follow exactly what I'm providing here. So for Mandani fuzzy inference system, user need to specify the differentiation type, and also need to specify whether the inference use cut operator or use scale operator to generate the output fuzzy set. Okay, so that's Mandalin's option, so we need to say. And for scanner, yeah, okay, scanner in its command we do have we do have option for the user to specify, right? Weighted average. Sure, the inferences use the weighted average or not weighted average. Okay, look into the equation. I mean, it's in the slide. You should catch up. I mean, the only difference is the difference is that you need to keep the firing stress somehow. If it is a weighted average, then you need to divide it by the sums of this weight. Just a little bit difference. Okay, so scanner and its command do have this option needed to be determined by the user. All right, so that is the entrance of fuzzy inference system model user need to specify. So if users again select scanner, then we provide this kind of equation selection for the user. If the user chooses Mandalin's command, then the page is hidden, right? So, well, again, that is related to the user interface. So for the assignment 6, what we are concerned is the input-output response surface. We need to generate that. Okay, so at final, I will show you how to use object-oriented technology to kind of save our model in text file. So later on, you can easily retrieve it and modify it, just like the modern application, right? For example, Office application, you can save your document, right? Save your document, save your PowerPoint. So you need to determine the format of your model, and then once the user click save, all this model can be saved. All right. So I do provide some simple model for you to verify your results. So let me see, where is it? Demo. Under demo, there is support a sample file. So we have, for example, oh, okay. So if you design safe and open functionality for your application, then once you use a special that file, you kind of read those input file and dynamically create universe, dynamically create fuzzy set according to the saved information, right? So this is, I think this is the example shown up in the textbook. All right. So, and then in the assignment 6, what we are concerned is that since right now we have 2 universe, right? So we have two dimensional universe. Then output is always 1 dimension. So we try to inference all crisp input. And if you click on this button, so the input-output mapping surface will be generated because it is 2-dimensional right? So the surface is actually the 3-dimensional surface, right? And this control is so-called T-chart component. It is a commercial one. And I have given you this dynamic link library. Today, I will show you how to use this chart component to display 3D surface. Actually, it's a 2D surface anyway, but in 3D coordinate system. Right, this is input-output response. So we have to generate that. So as you can see, right now we have 4 rules specified by the user: X, Y, right, Z. Okay, so this is assignment 5's requirement, right? We kind of inference. We let the user select a condition and then inference 1 condition there. Now, this is right now you need to submit the assignment 5. This is the actually I think it's a union of 4 rules. Okay, so remember the union 4 rules, but most of them the firing strengths are 0, so it's okay. So it's an example for Mandarin fuzzy inference system. And let us check another one. Example 4, figure 410. So this is a scanner fuzzy inference system. It's weighted average false, and then we have input 3 fuzzy set. Output we have 4 rule, right? We have 4 rules specified. So the output is an equation in scanner model. So right now we have shown up here. Okay, so the output Z is a little bit different from Mandarin and SCAN model. It is not a fuzzy set, actually is an integer. Indicator which equation is conclusion equation. So again, it's a 2-dimensional antecedent, right? Antecedent is a 2-dimensional universe. So again, the result or input output again is a 3D surface. So this one should be the input output response. So actually, as you can see, the input output surface is actually the intelligence of this system. We start from the user's definition about the fuzzy set, right? But the knowledge or the expertise will be expressed finally in terms of this input output surface. Probably it is not correct, but usually, I mean, the user can specify different kind of fuzzy set, the shape, different kind of parameter in order to make this input output response coincident with real world. That is another story. I mean, it's after you build up inferencing system, so you need to correct it somehow. I mean, in order to make it the accuracies and the correctness much more better than the first model. So that is the again, since right now we just have it, the input is a 2-dimensional fuzzy, so it's okay. And the last example should be SCAN model. I think should be SCAN model. So in this example, we just have one dimension, just have one antecedent. So the input output should be a 2-dimension, right? So as you can see, this part we can directly use our Microsoft chart to display the line shape, because input output relationship should be lines in 2-dimensional space, right? Small, medium. So again, we have 3 rules specified. And then after the inferences, oops, it's kind of weird. I don't know why. All right, so maybe something wrong here. I don't know. Let me try it again. All right. Anyway, I will look into this example on this. All right. So for assignment 6, we needed to try to generate the what? Because for this inference, we always expected that should be the CRISPR output. So the first thing is that we needed to add some functionality or property to our genetic fuzzy set. To that, the fuzzy set report COA, BOA, MON, SON, LON, this kind of value, because if we want, once we get the final fuzzy set, we needed to we need to perform differentiation operation, right? So in that case, we can define a function, or we can define a property too, just like the mathematical grid. Last time we added a mathematical grid, right? We needed that in order to inference as a rule. So it's about the time we add all this differentiation functionality. Either way, we can specify a function or specify that as a property. And the best way probably should be the property. We would like to add a property to our genetic fuzzy set. Again, we still use such kind of inheritance structure. So we put the general operation on the genetic fuzzy set. If the derived class has an obvious solution, they need to override this property. So the property, again, we will declare that as a virtual property. So then the derived class can override it directly. Okay. So I'm I will guide you through probably work on the first device education type. That should be COA, centroid or area. Okay, this is device education scheme. So, is there any question about the final goal for the assignment 6? We will complete our application. So that is the goal. I mean, in the first topic about the fuzzy inferences. Eventually, we will create this kind of fuzzy inferences modeling and execution system for the user. Later on, he can freely use that to construct complicated fuzzy inferences system. Okay, if you do not have any problem, we will start our assignment. So again, you need to clone your application. I mean, from assignment 5 into assignment 6. So I kind of use a work from a student here, right? Assignment 4, assignment 5. Do I have assignment 5? Let me see. Okay, it's assignment 4, right? 那张天恩在吗？你有 assignment 5的吗？上传好，那我用它 assignment 5，好，跟大家I will use this work assignment 5 we have. What do I have? Yes. 好。Okay, I kind of use 10 So you can start, cloning your assignment 6 from your assignment 5, right? So even though you have not completed your assignment 5, but you can, just follow the instruction I gave to you. Try to add it, because today we. Why? Do I keep it? Okay, suppose this is your assignment 6, right? After the cloning. So we need to incorporate the T-chart DL into your project. So that's the first step, because we need to use that. So from time to time, probably you might get some DLL from the internet, because if you look into so-called GitHub repository, probably a lot of project has been put there, and their DL can be shared with a lot with the public. So you might get DL for the .NET framework, and then you need to incorporate that with your user interface in the Visual Studio. So I'll show you how to do that. Okay, so right now our project is right here. So you have yours, right? So normally this is a file structure. So you have solution, you have your project, right? So before that, I suggest you probably add a folder, and I usually call it DLL used. So that means within this solution, you have probably more than one DL used in your project among this solution. So you need to copy the one I gave to you. So check out, it's from Cool. I did give it that to you. DL. Let me see. All right, so what you have is a T-chart RAR. So okay, you needed to shoot. And compress it first. All right, so you have T-chart XML, T-chart DLL. XML is actually a document related to the class and the functionality defined within this DLL. So you need to copy both of them to your folder. Okay, make a copy. So move, make a copy to your DLL user. So right now, our project can use this DLL to extend the functionality we have. Right? We need a charting component that can display the 3D surface for us. That is the purpose we kind of use the third-party DLL. So once you have a third-party DLL, you need to reference it in your project. All right, so back to your project right here. In your project, there has a category called references here. So that's a reference. So by default, what kind of dynamic framework class you have been using? Actually, there is an inclusion right here, includes a reference here. So as you can see, these are the logical category for the dynamic framework classes. So as you can see, we have a system, right? So your mass class has been located within this namespace system, and we have been using system.windows.form and other user interface, buttons, text box, all these classes are stored within this namespace. So the first thing is that we tell this project that we are going to use another DL dynamic hidden library. So click on this reference and then right-click it, right-click to add a reference. So reference means that our executable file will have a reference to other binary executable. All right, so different kind of category has been available right here. But what you need to do is that we definitely have a particular DLL to be invoked. So we use browse, select browse, and then click on this browses. So locate the DLL, the path of that DLL. So right here, this is the one. My project going to use it. So add it, t-chart. Make sure it is checked, and then make sure. So as you can see right now, our reference to add that t-chart, the name of that component is called t-chart. Right, so remove that. And t-chart, if you click on the main phone, right, in design status, usually we will see a variable control showed up in this toolbox, right? So actually, for the t-chart component, we do have several user interface we can drag into our form. So let us easily create the t-chart component for us, which will be similar to our Microsoft chart, right? So far, because nothing has been shown up right here, right? So I kind of unfold everything. So this toolbox actually is kind of goes, oh, okay, I don't know, maybe last time I have added it. Suppose I do not have this one, okay? I kind of remove it. So that would be the same as what you have right now. So the first thing is once we add a DL, we know definitely there are some user interface component within this DL can be assigned. Can be shown up right here. So that will let us easily drag that user interface component to our form. So the first thing you need to do is that create a tag, create a category right here. So move your cursor to this toolbox, this pen, and then right-click your mouse button. We try to add a new index tag. I don't know the English name exactly, so if you are using English system, you check that. Index probably tag or whatever. So type a name, probably I can call it t-chart. You can type any name anyway as you wish. All right, so we have a group, right? We have a group, right? But this group does not have any usable control. So drag one item to this, I don't know, maybe I can drag it directly. I don't know. I have not tried it, but let me do it to see if it is possible or not. So right now I kind of open our DL, right? This is our folder, right? So DL use. I don't know whether it works or not. Let me try it. Okay, I don't know. All right, so I kind of drag this D error into this area. Okay. All right, it's built in, right? So, okay. So I have. If I'm not doing it this way, let me remove it again. Let me delete it again, right? So let me try it again. So I add a new category. So I again call it T. Does not matter. The name is not important at all. Okay, if I'm not doing that in dragging, what you need to do is that click on this area, right click your mouse button, try to select items. I don't know the English command. Select item. So in select item, we need to specify that DLL. So again, you click on this button, browse. Navigate to your DLL right here. Click on this DLL. So we kind of select items from this DLL. The idea is that, okay, so the available user interface will be checked right here. So we have a bunch of available UI stored in this DLL can be added to our toolbox. So, okay. All right, so we have the available control shown up right here. So this is the general way. I mean, usually if you purchase a DLL from certain company, they will provide install procedure, do the procedure automatically. You don't need to manually add the available item from this DLL to this toolbox. If it is a third-party paid component, then they will provide installer for you to install this so-called .NET component for you. All right, but right now since we added that DLL by ourselves, so we need to manually add these items to our toolbox. Okay, so this is the first step, kind of here. And once you build up this kind of environment, you can exercise drag and drop the procedure, which is quite similar to the Microsoft chart. Okay. Alright, so I kind of share these parts. If I drag the most important component should be the T-chart. If I drag a T-chart in here, this is the initial look of this T-chart component. And sometimes we need another control. That should be the editor. Drag into it. Excuse me, not editor, sorry about that. Should be what? That should be chart control, cannot see it. Okay, chart controller, I'm sorry about that. It's not editor. It is called chart controller. So actually it's a toolbar. It's kind of toolbar. So once you drag into a container, by default, it will dock to the top. So never mind, I just leave it there. So we need to bridge them both of them together, right? So as you can see, this is the control bar, right? Control bar can control multiple chart, can control different kind of T-chart. So definitely within this controller, we should have a property can be specified, right? So chart, right here. So we have, okay, let's check about the name. Name is called T-chart, T-chart1. This is chart controller 1. So within chart controller 1, we can specify the property. That should be the chart. So system will look through the your main form, knowing that Yes, right now we have a component called tchart1 can be assigned to this chart component. So right now, both of them are linked together. So later on, you can select different kind of control button to control the chart right here in tchart. So once you drag the tchart into your phone, as you can see, there is a place you can access the property. Either way, you can just access the all the property settings from this property window, or you can come here. Excuse me, not here. Just direct click on it, and then right click at this tchart component. We have command there, edit. All right, so this is the editor for designing a tchart component right here. So it's kind of, well, might be overwhelmed, right? A lot of things can be specified within this tchart. But similarly, you will see similar terminology used in this tchart component, which will be a little bit similar to our Microsoft chart. You see, there's a series, there's axes, right? Series, there's a chart, right? So let us take a look at add. All right, so we try to add a series to this tchart. So we have all kind of standard chart, right? Pie, horizontal bar, another kind, and we also have 3D, right? So today I'm going to show you that we try to use the tchart to display a 3D surface, right? Actually, it's a 2D surface anyway in 3D dimensional space. All right, doesn't matter. All right, so this one is what we like to have surface. So select the surface. So we have surface one. It's a surface, and since it's a 3D-dimensional, right? So by default, this is the outlook of 3D-dimensional space. It is not in a perspective view. It is in so-called orthogonal view. It's an orthogonal view, not perspective view. So you can specify different kind of property right here. So because right now it's orthogonal, so it's look weird. It's not. It does not look like what we have seen in nature. So I kind of display this orthogonal, right? And then I can specify different kind of property here. So 30% increase the depths, and then we have zoom, right? Shrink it, and view angle. We can specialize some view rotation, perspective, view angle. Okay. More to that. All right, so explore the property setting. Through this in the editor by yourself. Okay, don't spend too much time on it because you might be confused. But at least you need to special axes, right? So axis is left axis, right axis. So left axis is the traditional axis, and the bottom axis pointed to the right. This is the bottom axis, left axis, right axis, and top axis. We have a top axis, depth, top, depth, bottom. So we have this kind of axis specified. But here we specify the bottom axis. So we have scale, title, tick, a bunch of property can be set. So we can set title. Maybe this is the universe, right? Input. So later on, you need to programmatically change that. If you get familiar with this tchart component, to make it consistent with your fuzzy inference system. In my fuzzy inference system, I might call it temperature or pressure, right? So you need to later on you need to do the programming by yourself, right? And the depth button, that should be the input universe. 2, right? And how about the left axis? Left axis is an output. Left axis is an output. For example, you have a temperature, pressure. It means your output should be power, right? So we kind of use this 3D service to indicate the input-output response, right? Okay, so that is the so programming you need to deal with is that you need to deal with this this series, but in contrast to a Microsoft chart, you can directly access this guy, service 1. So by the way, it's called service 1, right? So you can rename it. Just don't let the service 1 live there. Probably we'll call it maybe input-output response somehow like that. All right. Okay. I think it's 3:22 right now, so maybe let us take a break of 10 minutes break. If you did not catch it up, you can try to add this error to your project, okay? Or probably you can clone your assignment 6 from your assignment 5 and just do it in this break time. All right, so let us continue in 10 minutes, okay? So let us take a break. Okay, suppose right now we like to generate a surface on teacher component. Let me prepare a button here. So suppose this will be final inferences result. Okay, so I'm not going to do any directly subscribe this quick event right here. Okay, so when you click on this guy, we will specify the because as you can see, right, user may specify different kind of property. User may specify different kind of resolution, right? So that means 30 point by 30 point. I mean from the bottom axis and the depth axis, right? So it changes, right? So you need to pick up the resolution user want in order to do the inferences. All right. So I suppose right now it is determined, right? So if I have int, suppose that should be the width be into 30. Let me just D1 30, D2 maybe let it into 40. Right, so that's the resolution of the bottom axis and the depth axis. All right, so I need to prepare that service 1. Service 1, as I say, right now you can directly access that series. You don't need to allocate this series via this teacher at all. No, it's kind of different from Microsoft chart, right? So we can directly access that guy. So let us take a look at what kind of property can be accessed from this service series. Do we have points? No, right? Service 1, service 1. We do not have points, right? But we do have an add, right? You see, you have a lot of added functionality. So actually, since service does not have a point, but you can add that. And how about clear? Yeah, we do have clear. So that means clear all the point. So implicitly, there is no any property called point. If you like to see similar terms in with the Microsoft chart, no, we do not have a points correction here. And so for the teacher series. So let us clear everything first. And then we need to provide what? Series 1 X. Okay, let me look into the property windows first. So actually, you can set it in via this design property. So this is a service one. What kind of property we can set before we populate the point? We have a x value, y value, z value. Okay, we have two important property here. Actually, that's related to the resolution. Number x values. So x value actually that is the bottom axis. Z value should be the depth value. So these two should be our input universe resolution. So by default it's 10, right? So we need to rewrite it num x values. And also we need to set a property called irregular grid. By default it's a false. But we should say that yes, we should set that to true. So the property setting for this service, resolution-wise, you need to set it programmably. But this guy irregular grid, actually we can set it in the design phase. So we don't need to do any programming for this irregular grid. So you need to make sure irregular grid has been set to true, and you need to dynamically change this num x value. Number z value. Okay, so our service one x num and excuse me number x values. So that should be our D1. Okay, D1 should be the first. Well, we'll call it the first antecedent, right? The first input universe. Service one num z. So pay attention to that. The x-axis is the bottom axis. The depth axis actually is the z-axis. Vertical one is a y-axis. So you need to know that this kind of the default convention for that. So that should be D2. So we kind of set it, and then we will populate. So for example, double x from 0 minus 10. I will obviously create a service, show you how to do that. So x small equal 10. So you need to do it by yourself, right? So actually, you should pick up the first universe, right? First universe has minima value, maxima value, has its own resolution. So you need to do that by yourself. So but right now here, I kind of make everything's fixed here. So plus 0.11. So that's the x. And then another direction should be the depth axis. For double z, I call it z, maybe minus 5.0, x smaller than 5.0, y, excuse me, z small equal 5.0. Z equals z plus maybe 0.0, well, whatever. So it's about the time we find the inferences result, right? So since it's just think about that. X right now is the CRISPR value specified for a point inferences, right? In the first first antecedent, right? Z should be the CRISPR value on the second input universe. So we try to inference the result. I call it the result should be double y. And then I kind of use some triangular function to generate a random value. Okay, so mass sine maybe 0.3 times x. And then plus mass cosine maybe 4 times z. Anyway, let's just give it arbitrary value, x, y, z value. So once I get the point in three-dimensional space, I can add that to my service. So service 1, add. The add function, take a look at the information. There are 66 ways to specify the add, okay? So the one we like to have is just X, Y, Z, yeah, X, Y, Z. So we kind of invoke the 46 invocation, X, Y, Z. So I can add this point there. And I think that's it. So later on, you can use this kind of scheme to generate your input-output service, right? Okay. So let me just show you the result. So button is right here. Click on it. All right, this is our service. It's kind of answer, right? So these are the control for the T-chart. So if I click on this guy rotation, right? So drag it, you see the chart is rotated with your mouse movement right here. Okay, that is the way you generate a 3D surface on this T-chart component. Okay, so think about this kind of method. I think you still can spend a little more time explore all kind of property setting. Feel free to export that. But right now, as you can see, we do spatial. Well, this is input universe 1. Unfortunately, you cannot see the input universe 2. This is output units. So probably the temperature, pressure, power, such kind of things to make this chart meaningful. I mean, for your inferences result. Okay. All right. So this is how you use the T-chart to display a 3D surface. Okay. Is there any other question about this guy? Why we use it is because Microsoft does not provide a real 3-dimensional surface display. No. Okay. All right. So, is there any question about T-chart? So you still can explore all kind of possibility, all kind of property setting. Actually, this T-chart command is very famous. Okay. I think it's lasts up to date, maybe 30 or 40 years now. This company does not sell any big application. It just sell this kind of component, charting component. It can survive. It's a Spanish company. Okay. So you can Google it. I mean, from the internet. So the company name is Steamer company. So they kind of provide data visualization solution. I mean, for all kind of programming environment, T-chart. So buy its commercial product. So take a look at it. All right. So is there any question about the T-chart component? Because in assembly section you will be using it. If the rule, the number antecedent is exactly 2, so you will display that as a 3D surface. If the antecedent number is more than 2, no visualization is available, right? So only the number antecedent is 1 or 2. You can visualize the input-output response in a 2D graphics or 3D graphics. Okay. All right, so we will step into another topic about enhance our genetic fuzzy set, right? So it's about the time we do CRISPR inferences, right? So input is a CRISPR value, and we like to know the CRISPR output from the fuzzy inferences. So we focus on our genetic fuzzy set. So genetic fuzzy set right here. So we keep adding some property to it. Now once this is kind of so-called extendability. So pay attention to that. We are actually exercising the beauty of object-oriented technology. Object-oriented technology tell you that once you write an object-oriented application, then you will have maintainability, you will have extendability, such kind of thing. So we keep using that, keep using this OO technology to help us complete the final complicated software. So about the time we extended it. So there are both ways. Either way, you can define a virtual function to report the differentiation value, for example, COA, centroid or area, or otherwise you can use the similar way we kind of specialize that as a property, virtual property, mathematically, right? So here we like to use virtual property for that. So declare as public virtual. And since COA, BOA always return double, right? So I'll call it COA. If you don't like it, you can specify the full name, centroid or area, or differentified value. COA, differentified value, right? So this kind of terminology is related to fuzzy set. So number one, we just keep that COA. So you need to provide how will you get the value, right? So we add this part right here. So it's virtual. So user, the derived class should override it. So back to our genetic fuzzy set, right? Probably it is a function. Probably it will be a Gaussian function. If it is a Gaussian function, then what is the COA? The COA value should exactly its center, right? So okay, let me return 0.0 first to get rid of this red curly line. So once you define a virtual property, you need to think about the derived class. Should my derived class override it? Yes. For example, you are in this way in your Gaussian fuzzy set, right? Gaussian fuzzy set right here. The property is here. So you need to override what? The maximum degree by default is okay, but the property right here, we need to override it. So within the derived class, if you type override and type a blank space, COA is available for you to override it. So choose COA, hit tab key twice. This should prepare that for you. By default, it will inherit from its base class, right? No, it's not the way we do that. Well, actually, since it's simple, right? COA is what? Your parameter 0. Right? So you need to override it. Otherwise, the system will use the virtual function to do the calculation. It's really troublesome, right? So right now, if the derived class has obvious value for COA, they need to override it. So we don't need to waste computing time to compute the COA for you, right? But let us go back to our generic fuzzy set. How can you get the COA? You need to traverse, right? Traverse all the universe value, and in order to get the areas, the centroid or area. So how can you do that? It means probably you guys maybe not familiar with mathematics anyway. So usually, if you have a chart, 0 is right here, right? So you have a shape like here, such kind of shape. You need to find a centroid right here. So centroid point should be start with maybe minus amount. So how can you do that? So you will do integration first, right? You need to, so this is delta x, and then this is the current x value. So you kind of accumulate the value of this distance times this infinitesimal area together. So once you integrate, start from the minima up to maxima, so you will get what you will get the area times the distance, and then we divide it by area. So during the traverse, you need to calculate the area integration, the area of integration, and also the integration of areas times this distance. So finally, you divide it by that. So I will show you how to do that. But later on, you need to do BOA by yourself. BOA. So you need to come out an algorithm. The the algorithm should be different from each other. Don't just copy the algorithm from other students, right? You need to build up the capability to carry out arithmetic operation by yourself. So BOA, MON, such kind of differentiation value, you need to do it by yourself. Don't clone code from other students, all right? I hate to see just one version shared by all of you. Don't do that. You need to build up this kind of programming capability by yourself, all right? Okay, so I'll show you how to do that. I mean, basically, the operation is that since we have a resolution, right, we have an increment, right, especially in the universe, so we keep using that. The universe has specified the minimum value and maximum value and the resolution. So we use that to integrate the areas, not just area. We will integrate the area times the distance. So finally, we will get the COA by dividing the multiplication of distance and area divided by the total area. So that will yield the centroid, the COA value for you. Okay, so how can you do that? Again, we need the help from we need the information from the universe, right? So we start from 4 double x equal what? The universe, right? I don't know exactly now. Okay, the universe we know. Minimum value, right? Minimum value, yes. Excuse me. Start from the minimum up to where? X small equal the universe dot maxima, right? X plus equal, yeah, okay, plus equal the universe increment, right? So we always traverse our membership function with the help of the minimum value and maximum value resolution provided by the universe. Okay, so what we need, specify local variable double. So area time distance, right? So, all right. So areas accumulate, right? Actually, what we are doing is the computation of for area integration, right? So we will get members degree x, right? So that should be the height time the delta x should be the universe increment. So that is the infinitesimal area, right? Accumulated area. How about the areas times distance? Well, maybe we put a because we will repeatedly use that, so I hate to do the multiplication twice. So I use the multiplication once and keep it in the local variable. Actually, it's a block variable. So when this block is executed, this variable is accessible. Delta area times what? Times x. Right? Excuse me. Accumulated. So once we traverse all the points, so we have an area integrated, right? We also have an areas time distance integrated. So simply return what? Return areas time distance divided by areas. But be careful, probably area is 0. Will that happen? Yes. Area is probably might happen. So if area is 0, what value will you return? Minima, maxima, or the middle point? it's very interesting. I mean, you can make a decision by yourself. Okay, but since it's a COA, there is no any area, right? So, but you need to return a centroid distance value back to the caller. So it's really hard to make a decision. But again, because we have MON, SON, SLN, so we will, if areas really equal 0, then we'll simply return what? The universe maxima plus the universe minima divided by 2. We'll return center value back to the caller. Otherwise we return area time distance value. Okay, so you need to carry out. You need to design the procedure to compute the COA, MON, SON by yourself. So I like you guys to focus on your own design for computing BOA COA. So fine. Right now we have a COA ready. We used to do that. But when you look into this code, user can select, right? So if user select Mandani, right? So user will select a dephasification mode, right? So to support such kind of selection, the best way is that you define a new. So to let the user feel free to choose one of them. Okay, so it's about the time we add a type, a new type to your application. Okay, so maybe let's go back to our code. So it's about the time outside of this class. So this class we kind of add a public. You can name what kind of name you like, okay? But here I might suggest that let me check up the instruction suite. I have, excuse me, in order to so where is it? Assignment 6, right? Assignment 6. So in the instruction, what kind of class name I suggest? Okay, maximum value, COA CRISPR value. Fine. Maybe in order not let you confuse, so I kind of change it a little bit. Let me comment out. So back to our generic file set. If you want to change the name, don't change it one by one. You need to ask the help from the Visual Studio. Rename it. So I call it COA CRISPR value. Fine, it's up to you anyway. You still can keep COA, that's fine. But back to the Gaussian file, as you can see, right now the overridden COA CRISPR has also been changed. So this mechanism help you. So right now they are consistent, right? So virtual yet. So we need to have another system value equation. So one says that okay. I call it dephasification type. Dephasification type. Fine. So we keep using this individual name. So let us go back to our generic file set. In these areas, I add new public new. Declare that dephasification type, and here I might. So within a definition or a new, actually what you need to do is that you specialize the symbol. So the symbol must be an identifier. So identifier means that you cannot arbitrarily set any symbol started with any numerical value or any any symbol like that. So we'll call it COA, GOA, BOA, MOM, MOM, SOM, LOM. So right now, your system provides 5 different kind of differentiation type. So we have defined a new type. So it's very simple, right? We define a user's type called differentiation. We have 5 options. So intrinsically, it's a data type. By default, it's an integer data type. I mean, intrinsically deal by the computers. So again, if you like, you can specify the data type, maybe call it byte somehow, byte. So you just use byte to represent that. But usually we don't need to bother about that. So we use int to represent this kind of option. So COA is an option differentiation type. Okay, so it's a differentiation type. Then we finish in COA, right? So all right, so we're almost done. So COA is ready, right? Okay, so let us go back to our system label. So right now we need to define new class to include all these if-then rule, right? So let us first probably prepare the Mandani fuzzy system first. Okay, so we have the differentiation ready. Okay, BOA, MON, SON is your responsibility. So let me show you. Maybe it's about the time we create a fuzzy inference system class for the user to specify. So mathematically, BOA, Mandani fuzzy system. Okay, so we kind of extend our application by adding a new class, add class right here. Mandani fuzzy system. To think about the data structure a Mandani fuzzy system has, I think I have a suggestion right here. Okay, this is Mandani fuzzy system. Definitely, you have a list of rules, right? So either way, you can specify a fixed size array. So that means it's a fixed size array, or a dynamic list of array. It's all do. So anyway, so Mandani fuzzy system will consist a number of rules, fuzzy if-then fuzzy rule, right? And for this fuzzy system, the user want to interact with this system is that they want to inference some condition. So within this class, we provide this kind of interface function, fuzzy in, fuzzy out inferencing. So user need to provide an array of fuzzy set, that is condition parts. And then I will inference the result back to you as a fuzzy set, because it is a fuzzy in, fuzzy out inferences, right? If it is a crispy in, crispy out inference, the user need to supply differentiation type for me to return a crisper value to you, right? So similarly, we still need the conditional parts. So this function will be the public function provided by your Mandani fuzzy inference system for the user to interact with it. So eventually, in our main form, once we construct all the rule, right? Once we construct our rule, we will click on this button and invoke which function. I will invoke this one. Where we invoke this crisp in, crisp out. So I give you condition as a list of double, right? And I specify maybe a COA, BOA, and then you will return a double value back to me, right? So within here, right? Within here. So right now I have X value, Z value specified. In this case, I will ask the Mandani fuzzy system inference the result for this XZ. So I need to arrange XZ as an array and then invoke this function. So I will get a double back. I will get a crisper value back. So I will assign it to Y. So I will generate the input-output service from this code snippet. Okay. Alright, so this is our functionality, right? Well, to save time, I kind of lazy, copy everything. And then back to our our maintaining fuzzy inference system. Okay, copy in it. Alright, but if it is a fuzzy in, fuzzy out, what we return is a generic fuzzy set. So I kind of make everything clean up. Generic fuzzy set. So that should be a generic fuzzy set array conditions. Then I will return none. Generic, excuse me. It's a typo, right? Okay, so I need you need to finish this functionality, right? So crisp in again condition the classification type. To get rid of the red curly lines, I do have a return statement. Again, generic fuzzy set condition. Crisp in, fuzzy out, crisp. Okay, it's another option, right? So usually you will have fuzzy in, fuzzy out, but sometimes a user might special a crisp value as the condition. So again, what he asks is a fuzzy set output, so you will return a generic fuzzy set. How about the data? We need to have this data. So the data, what we have is just if-then rule. A set of if-then rule. If-then fuzzy rule. I think so. This years we kind of use different kind of name, right? If-then fuzzy rule. If-then fuzzy rule. So there's no need plural here. It's all rules. Okay, so let us back to the design constructor. So Mandani will provide this kind of interface function for the user to interact with, and the data require our own rule. So definitely, we will ask user CTOR, right, prepare a constructor for the user in order to create a Mandani fuzzy inference system. So the right way is that we ask this rule. All right, probably it's about the time. Usually, we will specify the argument. The name is the same as the data member. Okay, we remember that this is our data member. All right, so data member. So all rules is the data specified within the Mandani fuzzy set. How about this all rules? All rules is actually it's a local variable. But sometimes the local variable name is exactly the same as our member data, right? So in this case, you need to let the computer distinguish these all rules and this local variable all rules. So in this way, we need to use this dot all rules. Just copy the reference from the enter from the parameter right here. So all rules assigned to this all rule. So, and probably you might provide different kind of input in order to make your all rule array generate. So this is one constructor. Another constructor might this way. So you might let the user specify a dynamic list. This is dynamic list. Right? So it's a rule list. So you need to turn this list into your fixed size array. So how can you do that? It's not difficult at all. So all rules you need to instantiate with it, right? What is the number? Well, that should be the list count. Right, so you just copy that one by one from this list into your fixed array. So for int I start from. So if you are a guy who are familiar with C or C++, right now since you are using C#, so a lot of it's very sweet property can be directly used. So right now we do not know the number of element right now, right, in our old rules, right? So but actually you can always access the property, implicit this property there. So all rules, once it is instantiated, then the length property is available for you to loop through each element here. So I smaller than all rules length. So if it is a fixed size array, then definitely you will have property length can be accessed. So I plus, then you kind of assign all rules. Since they are reference type, so you need to copy the reference one by one into your fixed array. All rules, right? Excuse me, the rule list. The rule list is actually a dynamic list. You can directly access with this so-called indexer. So right now the right bracket is an indexer, it's an operator working on a collection of list object right here. But again, you don't need to specialize so much troublesome. You need to specialize all those codes. So actually, in fact, you can do what? If you look into the rule, the list, the dynamic linking list, there is a needy function called toArray. You see, toArray. It will generate a fixed array list for you. So we can directly assign that all rules. You don't need to dynamically create an array one by one, assign it. There is a public interface function for you to convert the dynamic list into a fixed size array for you. Okay, so now that's the beauty of anyway of the dynamic framework. Help us to do that. So right now, you kind of add a new system for you to do that, right? So how about maintaining fuzzy inference system, fuzzy system? The rule is different, right? So it's about the time we prepare if-then rule dedicated to the scanner fuzzy system. Maintaining system is okay, it's traditional fuzzy inference system. Fuzzy in, fuzzy out is usually, but it will involve defuzzification. Defuzzification computation is costly. So that is why we have a scanner and its model generated or created. Right? So we like to avoid the tedious or costly operation of defuzzification. That is the purpose for a scanner model and its model model. Okay. So as the instruction indicated right here, I cannot remember exactly where. Yeah. So we have scanner in the system. Okay, alpha function scanner should be hard coded, right? Okay, later on we will go back here. So we need to have a scanner if-then fuzzy rule, because the output is different from the traditional fuzzy if-then rule, right? The output is not a fuzzy set. Actually, it's an equation. By default, it's an equation. But right now, since we are not let the user arbitrarily set design this equation, so we kind of hard-coded our possible equation in our application. So we let the user select the index of the equation. So our scanner if-then fuzzy rule, the conclusion is not a fuzzy set. Instead, it's an integer. So we need to define that. So let us look into our traditional if-then rule. It's our if-then rule, right? So we have antecedents. It's a dynamic list. And if-then rule. consequence. Well, it's weird. It's not the one I have instructed you. Okay, consequence. Is that conclusion? Conclusion for this set? I'm sorry, because I think the antecedent actually is a list of generic file set, but the output, because the output is just one dimension, so usually we have a generic file set conclusion. File set. That's it. I don't know why you do this. We will not have a list of consequence. Consequence should be just a file set. We are not allowed multi-dimensional output. If you have multiple output needed to determine it, will be set up into a different kind of fuzzy inference system. In a fuzzy inference system, we just have one dimensional output only. We just deal with one output characteristic only. Okay, so go back to the instruction that I gave to you in assignment 5. So actually, this if-then rule is not the one I instructed you to do that. So never mind. I think this is, again, probably the time we take a break again. All right. So if you have any question, I mean, you can come forward. I will help you solve the problem. So let us take a break for 10 minutes. All right. Okay, so go back to assignment 5. I think in the instruction we do have correct if-then rule. The data structure within the if-then rule is just a list. That time we kind of allow the user to specify a list, a dynamic, because the user kind of dynamic and add a file set, right? So we accept that. So the data structure we specify in the if-then rule is a list, dynamic list, antecedent part, and the conclusion just have one generic file set. So that is the if-then rule. So for the scanner if-then rule, we added a new class for it. So we add class. So for this class, we are not going to seriously consider about the integration with the general if-then rule. We kind of make this rule as a separate class. So we are not going to construct a family of if-then rule. So call it scanner, right? Let me check about the name suggested right here. So we scanner if-then fuzzy rule. So I copy the name. So let's think about the data that should be embedded within scanner if-then. So we kind of copy this part, right? From if-then rule. But the conclusion is not a fuzzy set. So we are not going to specify the conclusion fuzzy set. We will use, because we kind of use an embedded equation, right? And equation will be identified by index. So we kind of index. So we might call it, I don't specify. So I get conclusion equation ID. Okay, that is the way we design our scanner if-then rule. When later, if you are familiar with the C# programming, maybe you can provide a user interface to let the user specify the equation freely. I mean, it's really freely. I mean, to that user, but you need to invoke the compiler, dynamic compiler, the code provided by the user to generate a dynamic link library, and then link that library with your executable code. It's a kind of technology-wise, it's not so hard to achieve that, but you will spend a lot of time in order to get familiar with that. So I'm not going to let you do that. So we kind of hard-coded our equation within this class. Okay, so that's fine. So once we let the user specify the equation ID, so we will provide this kind of function, get output value, right? So that means it's similar to what? Similar to the inferencing. So user specify the input, and then we will return it. Okay, let me see the instruction here. Provide for the user to select the output equation. This hard-coded function can get from this member function. All right. So since it's a member, right? So later on we will have an object or scanner if then rule. So that rule need to inferences. But here we kind of hard-coded our code right here. So we added this function. Oops. Okay, maybe it's the time we declare this one, because we have equation ID supplied by the coder, right? So we will make this function static. And let me move this static function in front of the data structure. So get output value. So and then user need to specify the equation ID. What's wrong here? So I need to add another parenthesis, right? So get output value, ID return, excuse me. And then since we have return, so we don't need to have break, right? But again, you have a default case, right? So we have default case. Return 0. So that will get rid of the red curly line. So we have public static function for all the scanner if then rule can use it. So from time to time, I mean, it's similar to the if then rule, right? So we have if then rule constructor. We have fuzzy in, fuzzy out inferences in rule, right? So definitely we will not have any fuzzy out, but we have fuzzy in. We might have fuzzy in, crisp out, or have crisp in, crisp out. So copy this kind of term, the name used in the function. So we return to our scanner if then rule. So what kind of functionality should provided by this class? Since we are scanner if then rule, right? So user might provide a list or a condition. So they ask for what? They ask for crisp out. There's no way we can provide a fuzzy out, right? Since we are scanner if then rule. So the only way we can provide is fuzzy in, crisp out inferences, or crisp in, crisp out, right? Or crisp in, crisp out inferences. If it is crisp in, then definitely user need to provide meet an int list. So either way, if it is a dynamic list or a fixed array, so okay for us. So since it is a fuzzy out, so definitely will return a double. You can only return double. All right. So how about fuzzy in, crisp out? This is the output, right? So get output value, input value, equation ID, So it's really straightforward, right? So condition. So condition should be the should match with our double, but right here we kind of use double. So it's still okay. We can convert that, but to be easier, I might change that a little bit into to list. Int input is the equation, right? So in this case, if user provide means a list of antecedent value, CRISPR value, I will simply call get output value. This condition, and then equation ID. What is your equation ID? Remember that is your conclusion equation. So the inferences is simple. I simply return this function call value. But how about CRISPR fuzzy in CRISPR? So user provide a list of fuzzy set, right? So how can you inference scanner output? I think you need to do that. So right now what you have is a list of generic fuzzy set. So you need to do the similar work, right? And again, I think the output should be what? Should get output, right? Get output. So antecedent. This is function output only. Okay, if you go back to the scanner rule inferences, the slide will show you that we will let the user choose weighted weight. Okay. The option is called weight. If you select a scanner model, user can specify is weighted average or simple average. Right. The average or weighted average should make a difference in the scanner fuzzy inference system, not in the rule. For a rule, inference is simple. I mean, we have input output, right? So we have firing strengths determined antecedent part, and they use that firing strengths. In scanner, we use that firing strengths to we do not use that. Scanner. I think scanner. Let me think about that. Scanner model. We might specify antecedent, right? So we can specify a condition, as I said, and inference that. But what we have should be a value. See, should be value. So we use antecedent to cut the rule. And we have mathematical way, right? So that will be the firing strength for that antecedent. The other one is, so we get the minimum value. We have firing strength for the upper rules. But in that case, what we needed to provide is an XY value. So that should be the X value and Y value. So to compute the output result. Okay, so that should be the intersection. Okay, never mind. I mean, if you go back to the slide, you will identify what kind of inference between. I mean, in scanner equivalent rule, if the antecedents is a fuzzy set. Okay, so you need to do that by yourself. I'm not going to implement that for you. So return double. So I simply return 0. You need to implement that by yourself. All right, so we have scanner if then rule already, right? So in that case, you can define your scanner fuzzy system. So how can we use that? So back to our application. So it's about the time we implement this function, main function, right? So in main function, when this button is clicked, we will create a fuzzy inference system first. If it is Mandarin, then we will create a Mandarin system, and then ask the Mandarin system to inference the output result for our crisp in, crisp out inferences. So let me go back to our main form. Suppose right now your application is ready for the user to create different kind of fuzzy inference system. So in main form, we might have a Mandarin fuzzy inference system. I might call it Mandarin system. And then probably we have scanners, Commodore will do that by yourself. So we have a user interface, right? We have radio button to let the user select it, right? Okay, maybe let me just complete this part first. And later on we will add another page for the scanner model to let the user select the output equation. So once this button is created, then construct the fuzzy system first. All right. So how can you do that? So suppose right now, since right now we are dealing with Mandarin system, so Mandarin system, we need to instantiate with that, right? But we need to prepare if-then fuzzy rule as an array or a dynamic list. Okay, so that is the requirement, right? So here we might prepare a list or what, or if-then rule. So what I'm showing you right here is for Mandarin system. If a user click on the scanner model, you need to prepare another block, okay? And this button is dedicated for 3D surface. And probably the rule just has one dimensional antecedent. Then in that case, you will not invoke this surface object at all. You might need to prepare another Microsoft chart. Okay, so remember that depends on the number of antecedents in your model. So data, right? Chart right here. So this chart, this chart and the T chart will not be pop up simultaneously. One will be hidden, right? If it is 3 dimensional, then we will pop up this T chart. Otherwise, it will pop up if the dimension is just 1 dimension. Antecedent, then this Microsoft will show up. These charts are added here in order to display the input-output response. Either way, it's a curve or a surface. So remember that just one will be displayed, and it's depending on the user specification. If antecedent dimension is 1, then we will draw input-output response as a curve in this Microsoft chart. If the dimension is 2, then the input-output response will be 3D, so we will use this T chart. So remember that this button will need to make a lot of decisions. So these parts are just for 2-dimensional antecedent. So to create a Mandarin system, we need to prepare if-then rules. So I call it rules. And since it's a dynamic list, so you need to create it, new it. individual certificate use. So we have rules, right? So you kind of loop through what? Loop through your grid, your rule grid right here, if then rule. Right? You need to loop through this guy, DGV rules. Basically, that should be one. Smaller than the DGV rows. That rows. The data grid view has a row count for you. So R++. So with this rule, actually we'll add one rule, right? So at the end of this guy, ULES will add an if-then rule. So within here, you will prepare if then rule, a rule. So what does rule need? Antecedent list and consequence, not the list, okay? So we need to change that a little bit. This is not the case we have, so we will have the constructor asking for a list of antecedent and a generic fuzzy set for our conclusion. Antecedent part, conclusion fuzzy set, equal conclusion. That's it. This is the constructor. The correct constructor we specify in our if-then rule. So loop through each row in the data grid view, you construct a rule, right? So we kind of prepare a list of fuzzy set, generic fuzzy set executed. And okay. Actually, you don't need to repeatedly create this rule and move it to the outside. Right? But before a rule, right? Before a rule created, I can antecedent clear. And then I look through each column. C start from 0. C some DGV rules. Columns count -1. Why? Because the last column should be our conclusion fuzzy set, right? So all right, so add fuzzy set. So where did you get the fuzzy set? Well, it has been stored secretly under these DGV rules. Rows are as rows that cells. C, this cell, that tag, right? So antecedent add that. But since your antecedent is what? Antecedent is a list of generic fuzzy set. The tag, the data type is object. So we know definitely that should be a fuzzy set. So we can cast. We use S to cast that generic fuzzy set. I don't care about the real type of that fuzzy set. Probably it is a triangular or Bell or Gaussian. It doesn't matter. They can always be regarded as a generic fuzzy set. So that is the beauty of algebraic inheritance mechanism. So we added antecedent added conclusion. And how about a conclusion? Well, conclusion, maybe I don't need to prepare that. So I create a rule via this antecedent. How about a conclusion fuzzy set? It's a generic fuzzy set, right? So I can directly use the DGV rules that rows that are cells. DGB rules column count -1. It's kind of lengthy, but be careful. I'm using to specify the index correctly. The tag as generic fuzzy set. So you know what I'm doing? I just pick up the first column, second column. If they are two dimensions, so these two columns should be the antecedent part, and then the last column should be the conclusion. So I kind of traverse one rows from this data grid view to construct a rule, right? So back to the back to our main form. So because main form, the data grid view is a component of main form. So main form within this button click event, we can access the DGB, pick up the fuzzy set specified by the user, and construct a rule right here. Construct a rule. So once a rule is constructed, it can be added to this rule set. This rule added to this rule set. Okay, so for this part, we simply traverse all the rows of this data grid view. So we complete the antecedent. Well, I have error. Let me check it out. We need to have semicolon attached. So we have a rule generated, and then we kind of complete the antecedent, the rule. Excuse me. If the rule. Antecedent, clear. So a rule generated. Then it's about the time we construct a Mandana system. Again, because our rule is a dynamic list, right? So, but the constructor asks for a fixed size, so you can convert it. Or otherwise, we invoke this one. We invoke a list of if-then rule. This of if-then rule. So you design that you should provide different kind of you should provide different kind of constructor for the user to easily to construct a Mandana fuzzy system. So then I can just put rules in it. So it will be done. So right now my Mandana system is constructed before user click on this button. So once this because the user might keep changing the rule setting, right? So the updated rule will be shown up within this grid. So once the user try to generate the input-output response, hit this button, we will construct the Mandana system again first. Actually, we updated our Mandana system, right? So we update our Mandana system right here. And then this button will be invoked, right? So we actually ask a Mandana system, crisp in, crisp out inferences, right? So if we know it's two-dimensional, right now, suppose it's two-dimensional. If it is two-dimensional, if it is one-dimensional, you need to run another code. So right here, we suppose the antecedent is two-dimensional, so it will generate a 3D surface, right? So right here, well, how can you get y? So y will be obtained from where? From this Mandana system. Mandana system. Inferences, crisp in, crisp out inferences. So how about the condition and the type? User need to surprise the type, right? So what about the condition? Condition should be wrapped up with these two, because definitely this inference is two-dimensional, right? So the zeroth crisp value is x. The first crisp value is z. So we need to prepare a double array. I'm gonna call it the inputs anyway. So definitely we know it's two-dimensional. New int extreme double 2. Okay, so x1 input zeros should be the first crisp value, means start from x, right? And this input 1 is Z value. So the CRISPR value in the first antecedent universe, second universe, since it's two-dimensional. So we have input value specified. And then we invoke this Mandana system, CRISP in, CRISP out. So Mandana system up to this point is a complete further inference system. Right now we will invoke its public function. We give it a CRISPR, a list of CRISPR value, and then it will return a CRISPR value back to us. But since it's a Mandana, the output normally will be a fuzzy set, right? But we ask for CRISPR out, so we need to specify the type of defuzzification. So right now here we supply that input, and then we need to choose the defuzzification type. So up to this point, IntelliSense has highlighted this enumeration. Actually, this enumeration is created, is defined by you, right? So we simply hit the dot key. So suppose I choose COA right here. So that is the way we generate a point on the input-output surface. So we have Mandana system constructed, then we invoke its CRISP in, CRISP out inferences. We supply a pair, actually it's a list of input value. It's a double array. Then we specify the type of defuzzification type, and we get an output CRISPR value back. So we plot it as a point in this surface. So then we finish the plot. So what I was showing you right here is dedicated for two-dimensional antecedent and for Mandana system. But remember that this button right now is for this 3D chart. You might prepare another button anyway for these two. If the input-output, if the dimensional antecedent part is one-dimensional, you might prepare another similar button here. Or probably you lump sum both of them together within this button. So this button will deal with one-dimensional and two-dimensional input-output service or line generation. But that will complicate your algorithm, and as you code it here. So that feel free to do that. Well, I think in my demo app, I kind of use different kind of button, right? So if it is two-dimensional, right? Since it's two-dimensional, so I have this button inference, right? And if this button is for T-chart, for three-dimensional display. And how about if I kind of delete one? So it's turned out to be one-dimensional, right? So that should be one-dimensional. And I'm not going to do that. So let me bring back the Mandana system again. So this Mandana system is two-dimensional, but if I erase one universe, so you see my ruler also reduced to one-dimensional ruler somehow. Then I can. This button is dedicated for one-dimensional input-output response. So we have a Nigeria. So well, just you can prepare two buttons. I mean, one is for one-dimensional input-output response generation, the others for two-dimensional. Okay, so that will be much easier for you. But what I'm showing you right here, this button is dedicated for two-dimensional for the service generation, and that is particular for the Mandana system. Okay, so just follow the similar structure. I mean, to create your scanner fuzzy system and Tsukamoto fuzzy system. But again, we still have one thing missing, right? We need to prepare a user interface for scanner model. So scanner model, you need to provide an additional page. So let us go back to our tab control. This is our tab control. So normally, up to this point, we have two pages specified. So we will have add another page. So this time, I name it because programmatically, we need to access it. Okay, so I call it page scanner. as scanner, right? As scanner. Confirm. Or let me change the face text. Scanner output equation. I might not call it output conclusion equation. Okay, and within this page, what we provide is just a list that the users choose. So I might use list box. So within this box, okay, just add it. Yeah. So if it is scanner model, then if then rule, I'll put equation right here. So I kind of use this message to let the user select. But again, it's L prompt, easily L prompt, because if the user special 2-dimension, right? So if it is 2-dimension, definitely they should select either 3, the third up to 6's equation, because it involves 2 x and y variable, right? If it is 1-dimensional, the user can only choose 0, 1, or 2, not 3, 4, 5, because 3, 4, 5, 6 are for 2-dimensional cases. So user need to carefully select the output equation ID carefully, by looking into this list. Okay, so how can we use that to construct a scanner user rule? So if you use a special scanner fuzzy model, they kind of add the input universe. If it is 2-dimensional, output always has one universe. So in this case, use a special L, special Gaussian triangular. So normally it's what? For the antecedent part, it's okay. It's just fuzzy set selection. How about output? So output should be equation. So when user construct if-then rule, the conclusion part will be a little different, right? So if user, I need to do special output for this set in order to make this button a variable. So output universe for this set. You see, once I click on fuzzy set, right? So I'm not going to let the user add fuzzy set parameter, because scanner model, the output is an equation, not a fuzzy set. So once the user click on the output universe, the user can select right here. All right. So for this output, since this is 2-dimensional, so I can choose 3, add equation 3. Oops, kind of fail, huh? 4, 5. I don't know what except it came out. So that is the way you model a scanner model, right? Input is a fuzzy set, output is an equation. So we simply choose the index. So actually, what hidden in the tag of this tree node is actually an integer, just integer. Okay. So we agree that we have sets of equation hard-coded in our code. So user need to specialize just in the index only. So within this tag, within this tag actually is the index. Okay. So and then user try to construct scanner if-then rule, right? So interesting. Why I cannot edit. Why? Scan on using bell, equation. Oh, it does not work anyway. So I don't know why. Sure, let me edit. So why I cannot edit? Okay, I'm sorry about this. So maybe I will try it again. Quickly try it again. Maybe this error generates this kind of problem. I don't know. So let me do it again. I mean, if it fails again, so I might try to fix it and then show you the procedure of creating a scanner model. So I have a scanner model. Suppose right now I kind of use one-dimensional scanner model. So I have this one. I will set for this there, and if I choose output, what I can select is just one, add one. Main phone combo. Alright, definitely I have a problem. Anyway, I just load from the saved file. Okay, so let me open this scanner model here. Okay, so we have, actually it's a two-dimensional, right? So it's two-dimensional. So how about rule construction? So right now I can add a rule, right? So normally is so if I delete some rule, let me delete it. Can I delete it? No, I cannot delete it. Interesting. Can I add it? So if a user add a rule, right? So it click on the actually in your model you select fuzzy set, select fuzzy set, and click on this cell, right? So that is the way you define a rule. And the last part, I'm sorry, because I kind of use combo box to do that. So in here, you need to select pop-up equation, right? So if I select this equation, oh, the equation is not listed right here. All right, because I kind of hide it because I kind of use combo box to let the user select it. So I'm sorry about this. This version is not for your current practice. So I might shoot another video to tell you how to do that. Okay. Sorry about this. Okay, so what's left for the scanner model is that once the user want to create a rule, the antecedent part is the same as the Mandana system. He kind of select the fuzzy set and click on here. So the similar operation will be done. For example, just user select the equation, right? Select equation, and then click on this this antecedent part. Let me try to change it. Excuse me because I kind of use combo box, so forget about that. So normally, in your application, you should let the user specify the equation on their output equation list right here. So user press on. Let me go back to our example right here. So if it is a scanner model, user will create a rule. I'm sorry, this interface is not for the scanner model, right? So, okay, remember I will prepare a video clip telling you how to set up this list and then let the user construct their if-then rule via a click. Actually, it's not so difficult at all. Just remember that because you have a bunch of fuzzy set special in the universe, right? So the similar way is that you click on the output universe, and then you came back to this scanner event. You click on first equation, second equation, and then the first equation will pop up on the label of fuzzy set, right? Similarly, you will see equation 1, equation 2 in the child tree node here. Okay, let me prepare another clip for you. All right, so for scanner model is a little bit difficult for us. So again, this function. Let me check about this function first. So in scanner model, in the scanner if then rule, we will provide this function. So you need to hard code it. For example, if a user give me a set of input, so input 0 plus 1 is for 1 dimension, right? So for 2 dimensional, for example, if the case 2, you need to implement that here. And then you need to prepare a text, right? The text right here. So for example, if here, the first one is y, so 0. So go back to your list right here. In items, you will put this indicator 0, y equal 0.1x here. So similarly, just prepare this kind of list. So later on, if the user want to specify the output equation, when user click on the output universe, and user will click on this one, you will keep changing the tree node is under this output universe, right? So the user select the equation ID for his scanner output equation. Anyway. Okay, so probably that will be all. For the Tsukamoto model, well, actually, if user select a Tsukamoto model, when user click on the output, you can let me see if I really provide such kind of mechanism or not. So if it's Tsukamoto, right? Tsukamoto. So the requirement is that the output fuzzy set must be what? Monotonic, right? So output universe, why I do not have? Okay, let me open that Tsukamoto model here. So this model is simple. We just have one dimensional antecedent, right? And how about the output? If a user click on an output universe, so user try to add an output fuzzy set, right? So you should prohibit, for example, bell is not a monotonic fuzzy set, right? So if you use click on a bell, excuse me, you will not let that happen, right? Try to add it. The selected output fuzzy set for its Tsukamoto model is not monotonic. It's okay, but it's not good at all. So it is better that, once you use a selected Tsukamoto, the available primary fuzzy set will be filled. For those, fuzzy set, primary fuzzy set, which are monotonic. For example, sigmoid or left shoulder, right shoulder, S function, G function, like that. So, which means that how can you achieve such kind of filtering operation? What do you need? Property is another property added to your generic fuzzy. So let me finish this one. So if you go back to the generic fuzzy set, we might provide again a property for your code to identify whether this fuzzy set is monotonic or not, right? So back to our generic fuzzy set in our property, in addition to COX value, we might add what? A public virtual, excuse me. 4 is monotonic, get. By default, is false. So who needed to override it? Those fuzzy set which is monotonic, right? So later on you can check the fuzzy set whether it is monotonic. If it is monotonic, and then it will appear on the list. Not that the user chooses it. If it is not monotonic, then definitely it will not appear on the list for Sakamoto model when user click on the output fuzzy set selection. So similarly, it's monotonic. If in your by default it's false, right? So everybody inherit from that. But for your sigmoid fuzzy set, you need to override it, right? So in your sigmoid fuzzy set, you will overwrite blinker character. What's wrong? Actually, put it in the right place. Override it. Is monotonic. I return true. Right? Because sigmoidal function is monotonic. So later on, you can use this property to screen out those fuzzy sets which are non-monotonic for Sakamoto construction. Okay, so keep expanding the functionality or properties or even events on your generic fuzzy set to increase the capability of your fuzzy set. All right, so that is the beauty of so-called extendability for the object-oriented technology. Okay, I think that will be all for today's lab time. Is there any other question? I know it's kind of a little bit fuzzy. I mean, for the Sakamoto modeling, but try to complete the modeling capability for it. Okay. So what's left should be the file, the model saving, and the open it. So that will be covered in an extra video, I think. So I will prepare another video clip to show you how to save your Mandani system, Sakamoto system into a file, so later on you can easily retrieve it. So the final goal is to evaluate your assignment. You need to, as the instructions say, you need to prepare a video clip. Okay, so videotape the execution of each model to show the modeling and inferencing capability of your application. So basically, I'm asking you to run the example in the textbook. So that should be we have 3 example for different inference system. One is for Mandani. So you need to test that. This is the first example, right? It's a Mandani system. So we tested your application to see if your application generates similar input-output response surface. Okay, so this one you need to verify it. This example, and another example is for scanner model, 2-dimensional scanner model. That should be a 3-dimensional space. The last one should be Sakamoto 1-dimensional inferences result. So that should be a result. So make sure your application can generate the exact solution as that shown up in the example to show your application to generate the correct fuzzy inferences. Okay. Right. So if your code is working well, then you can try build up this kind of complicated fuzzy inference system. Remember that we have an example, right? This example is in the literature, so it's a famous literature. So totally there are 49 rules. 49 rules generally. And but the conclusion part maybe just 10 or 7. I cannot remember exactly. So input, 2-dimensional input. Output is one also. As you can see, it keep using a lot of triangular fuzzy set, and then left shoulder or right shoulder fuzzy set to construct smart vehicle tracing controller. Right. Okay, so that will be the final goal for our assignment 6. Okay. So start from today, maybe you just have 11, I think 11 or 12 days. Yeah, so keep going anyway. All right. So we will end up right here. Is there any other particular problem or question up to now? All right, that's it. Okay, for today. So